So single slit interference is a little crazy because you're getting an interference pattern from seemingly one source, right? Double slit interference kind of makes sense because those two slits, right? Like if I know it's kind of hard to see because this whiteboard reflects, but there's these two blue waves, right? They're coming straight into, and I can add a barrier here to make it a double slit, right? So I have two small slits, and because these slits are very small, they act as point sources by Huygens principle, right? Because all these barriers are going to block off this part of the wave, but there will exist waves right here, and they're going to, by Huygens principle, act as like sources of like wavelets and be point sources of new waves, and you get an interference pattern because that makes sense, right? There's two waves, and those two waves, they're interfering with one another, and by the time you get to the screen, right, you will have certain maximums, certain minimums, and as a result, you'll see destructive constructive interference. That explains the bright fringes and the dark fringes. But single slit interference to me was initially really confusing because it's like you have only one source, right? Like, doesn't, obviously, like, this is just one big slit where the waves are going to kind of bend around, right? Isn't that what we would expect to see? And for really, for, I guess, bigger slits, the idea is that, well, if you have a wave, right here, this slit's pretty big, it's going to have multiple kind of point sources. One may even say an infinite amount of little point sources right here. And they're going to create waves that are going to interfere with one another and cause those interference patterns. That's why we see single slit interference in the first place. So in that case, that's, how can we like model that, right? Like what would single slit interference look like? And essentially what you get, and by the way, I watched a video by We Are Showboat on single slit interference. Great video. I'm kind of just, it's going to be very similar to his video, but I'm going to kind of interject with my own thoughts and stuff. The interference pattern you're going to get, it's going to kind of look like this. So you're going to have these fringes, and I drew this terribly because the slit's right here. If this is the middle, you're going to have these fringes, and you're going to have a really big bright spot, and then more fringes. And the idea is that we are going to have these minimums right here, right? So with the double slit experiment, or with more specifically like diffraction grating, you get really pronounced maximums, right? If you saw the diffraction grating demo, or if you saw the double slit interference, like the slits, like the bright fringes are very clear, and then the minimums, right? Like the dark fringes, they're kind of more spaced out. Like it's not really a distinct point. You get kind of the opposite with single slit interference. You get kind of like minimums that are very pronounced, and then the bright spots are more smeared. And the reason for this is because when we get bright spots at constructive interference, right? But at these bright spots, I guess I should explain first. I should explain first, or kind of show the math behind the dark fringes. So, there's an infinite amount of point sources here that are going to be creating waves. Let's boil it down to 6, or let's do 7 or something, just so that, we're modeling this, right? It's just a model. And it's going to have 1, 2, 3. Oh, I'm drawing this terribly. I guess I should draw 1 here. So that's 1. And then I have 3 on each side. Whoa, I'm kind of an artist. Look at that thinking. Okay, so 7 points that we model as like point sources. They're going to be radiating waves. And I can draw lines to show the direction, right? So I can draw a line from this top one to the minimum to kind of show the direction that the wavefront would travel, right? So remember, I'm not saying that waves are I'm not saying waves are lines. I'm just saying that, this is the path that the wavefront would take to the minimum. And I can take, in order for there to be a dark spot, all of the point sources have to kind of cancel each other out. And that's a pretty hard thing to really prove. So, because to kind of prove, or you can't really prove anything in science, but to kind of confirm that they're all, canceling each other out, there's an infinite amount of point sources. So how are we gonna go about doing that? We just gotta look at 2, right? Think about, and I'll show you why we can look at 2 and then apply everything else. Think about this point right here and the point by the barrier and the middle point, right? And the middle point, they're gonna interfere like this. And it's gonna be destructive interference. So if this is D1 and this is D2, I can do my small angle approximation where I can draw a line, and I can draw a line that I think is like a perpendicular bisector or whatever. I'm just making a line that creates a right angle, so I can create a right triangle. And for very small angles of theta, which obviously we see with diffraction because the screen is super far away and it's much larger than the slit width. We can say that this side right here is equal to the path difference. In other words, the rest of the length of D2 is just equal to D1. So from the perpendicular line to there, they're equivalent, which we can say for small angles. And it's just like double slit interference, but instead of this being D, like the width, or the distance, the width, the width or whatever, we're actually gonna say that this is or not width. What am I saying? Instead of saying this is a distance of separation, we can call this W over or A over 2, right? I'm gonna say A for the total width, right? The total width is A for the slit, but there's A over 2. So I know A over 2 sine theta is equal to change in D, because if this is excuse me, if this is the angle theta right here, you can use trig and show that this is true, just like with the double slit interference. And in this case, well, A over 2 sine theta has to be equal to some multiple of m, or I guess lambda over 2. Because in order to have destructive interference out of phase, when you start in phase, right, because everything's hitting the slit simultaneously, you need to have this kind of relationship right here where you have that in phase, out of phase path difference. With that, you actually get that A sine theta is equal to m lambda, right? In this case, we're looking at kind of the first minimum, so this would just be lambda. But yeah, you actually get A sine theta is equal to m lambda for minimums, which are for, I guess, minimums and destructive interference, which is kind of crazy because usually this is for constructive interference. But because we're looking at like these 2 points right here, they do start in phase and they end out of phase, so we can use m lambda over 2 for our path difference equation, but then the 2's drop. So this, I guess, really isn't the path difference equation right here. This is just a simplified version of that allows us to relate the wavelength, the maximum, or the min number, sine theta in A. And then, of course, just like usual, or to kind of show that this is indeed a minimum, you can just go a wave down and do the same exact thing. So I can go a wave down here and a wave down here, and I can show that this would still hold true because the sine theta, when I do the derivation, do the same thing with my perpendicular bisector, this marker's kind of dying. This theta is so small that the sine thetas are essentially equivalent because these lines are essentially parallel. So it's like the same angle as you go down the slit because of that small angle approximation, because the screen's so far away from the slit. So yeah, that's why there is a destructive interference here, because each wave cancels out the other. And this doesn't have to be a over 2, right? This could be a over 4, right? You can go quarters, you can go eighths, sixteenths, any even number. And because you're dealing with an infinite amount, as you make that fraction, like if you're comparing, right, a over 1,000 or something, right? Then you're comparing essentially waves kind of right next to each other, and you're going down the line. Well, that means you can prove this for all the point sources. You know what I mean? Like you can poo. Wow. Okay. Poo. Haha. I don't know why I'm like stuttering so much. I'm like, I don't know, but you can prove that there's destructive interference where each point source cancels out all of the other ones, right? That's why we get a perfect like dark spot right there. So that's single slit interference in a nutshell. Obviously, if you're changing it and doing it to like, oh, I'm gonna go a over 4 and check and do my derivation like that or whatever, then you just gotta change this to a 4, right? And then this becomes, instead of, this will become 2m lambda, right? So this 2m, what this actually tells us is that m can be an odd number, right? Because minimums occur with like your 1, 3, 5, all your odd numbers right here. But then when you take an odd number and multiply it by 2 or an even number, I think by an even number, it'll also become even. So this a sine theta actually holds for all like integers, right? So m can represent an odd integer, it can represent an even integer. It just can't represent 0, because at 0 we actually have a maximum, like we have a bright spot, so we can't have 0. We can't have 0, but we can have 1, 2, 3, 4, 5, and so on. And yeah, like that, this is just single slit interference. You can do your approximation where you can say, okay, well, this is L, this is Y min, sine theta is approximately Y min over L, so you can get your A Y min over L and do your math. But this is just, I guess, an introduction to single slit interference, at least hopefully making it make more sense, because, it doesn't make a whole lot of sense, the idea that a single slit can cause interference patterns. So yeah, thank you for watching.